In this section, we're going to be looking at hypothesis tests for a population proportion. Now, I mentioned previously that the mathematical logic for doing a hypothesis test for a single parameter is the same as the logic that we used in the previous chapter for confidence intervals. So that is true here with population proportion. A hypothesis test for a population proportion is going to be based on a normal distribution, provided that we have the characteristics that we can use to model a normal distribution. And so those characteristics are as follows. The sample has to be obtained by simple random sampling or the result of a randomized experiment. The sampled values have to be independent of each other. And so we're going to check that by making sure that the sample size is less than or equal to 5% of the population size. And then last but not least, n times p times 1 minus p has to be 10 or greater in order to be able to say that we have a normal distribution. So as long as we meet these criteria, then we'll be able to do a hypothesis test by using a normal distribution as the model. Definition. When observed results are unlikely under the assumption that the null hypothesis is true, we say that the result is statistically significant and we reject the null hypothesis. So again, we're saying the observed results. The observed results are the results that we're seeing in our sample. So we're going to take a sample and we're going to see what the results are in that sample. And if the results we obtain from our sample would be unlikely under the assumption that the null hypothesis is true, then we're going to say most likely that would not be true. We would not get the results that we're obtaining if the null hypothesis is true. So therefore, we're going to reject the null hypothesis. Most likely, the null hypothesis would not be true, or we would not be obtaining the results that we obtained. Anyway, if we do, we're going to say the results that we obtained are statistically significant. So keep that term in mind. Statistically significant means that we most likely wouldn't get the results we obtained if the null hypothesis is true. So the results that we obtained are statistically significant. Significant enough that we believe that the null hypothesis is not true. So the classical approach for conducting a hypothesis test for a proportion. If the sample statistic is too many standard deviations from the population parameter stated in the null hypothesis, we're going to reject the null hypothesis. And so again, that would mean that the sample statistic that we obtained is statistically significant if that's the case. So again, what we're going to do is we're going to find our sample statistic, and if that sample statistic is too many standard deviations from the population parameter that's supposed to be true as stated in the null hypothesis, then we're going to reject the null hypothesis. So this will make a little more sense if we take a look at an example. Eating together. In December of 2001, 38% of adults with children under the age of 18 reported that their family ate dinner together 7 nights a week. In a recent poll, 403 of 1,122 adults with children under the age of 18 reported that their family ate dinner together 7 nights a week. Has the proportion of families with children under the age of 18 who eat dinner together 7 nights a week decreased? Use the alpha equals 0.1 level of significance. So the alpha equals 0.1 level of significance means that we're risking making a type 1 error with a probability of 0.1. Now, when we conduct a hypothesis test, the first thing that we're always going to do is choose the null and the alternative hypothesis. So our null hypothesis in this case is going to be that the proportion of adults with children who eat dinner together 7 nights a week is 38%. So this is what has historically been true, or at least that's what was true as far as December of 2001. So that is our null hypothesis. So we're assuming that it's still 38% unless our evidence convinces us otherwise. So our alternative hypothesis is going to be P, and we're going to have 0.38. And so the question is, do we want less than, greater than, or not equal to there for our alternative hypothesis? And the way we're going to determine that is by the question that we're trying to answer. So the question was here: has the proportion of families with children under the age of 18 who eat dinner together 7 nights a week decreased? So has it gone down? Is it now less than 38%? So what I'm really saying with the null hypothesis is that the proportion of families that eat together 7 nights a week is still 38%. And then the alternative is that the proportion of families that eat together 7 nights a week is now less than 38%. That's what I'm saying with this null and alternative hypothesis. Now the second thing we do is we choose a level of significance. Now in this course, you're going to be told what to use for the level of significance. But in real practice, you have to make that determination for yourself. So no one's going to be looking over your shoulder saying, I think you need to use a specific level of significance. You have to make that decision on your own. Well, we choose a level of significance based on the seriousness of making a type 1 error. So how serious would the error be if we reject the null hypothesis when the null hypothesis is actually true? Well, if there would be really bad consequences of making a type 1 error, then we would want to use a much lower level of significance than 0.10. So we're risking it with a 10% probability. So if there was like a really serious consequence of making a type 1 error, we would want to use something like 0.01 or 0.05. And 0.05 is the most common level of significance to use, but 0.01 is used quite a bit also. But we could really theoretically use anything we want for that level of significance. Anyway, in this case, we're instructed to use a 0.1 level of significance. So, how is this going to work? Well, with the classical approach, I'm going to begin by thinking about the normal distribution. And I need to make sure that I'm going to be able to use a normal distribution to model this scenario. So I have to make sure, do I have randomness? Well, it says in this particular case that we had a recent poll. 403 of 1,122 adults reported that they ate together 7 nights a week. Well, it doesn't specifically say that they use randomness, but I will assume that they randomly selected these 1,122 people so that we do have randomness. Secondly, we have a population of adults, and we have 1,122 of that population of adults. I don't know what the exact population of adults is going to be, but certainly 1,122 is less than 5% of that population, so certainly we have independence. And so the main thing that I need to check is N times P times 1 minus P, is that 10 or bigger? Now the P that we're going to use here is the P from the null hypothesis. And so we typically are going to call that P with the subscripted 0. We call that P naught. And so that is the P from the null hypothesis. So in this case, my N is 1,122. The P from the null hypothesis is 0.38. And then 1 minus 0.38. Well, if I bring in my calculator here, 1,122 times 0.38 times 1 minus 0.38, that is 264 plus. So that is 264.3432. Well, that's certainly 10 or bigger, so we meet our conditions to use a normal model. So, in this particular case, we have a left-tailed test because our alternative hypothesis is less than. So we're going to be interested in this left tail. Now, the level of significance is going to be this area in the left tail. So what we're going to do is we're going to find the critical value that separates this area in the left tail, this 0.1 in the left tail, from the right. Now, we've learned in previous chapters how to figure out what this value is. We've had several options. I could use the standard normal table from the book. I could use the inverse norm command on my calculator. I could use the normal calculator in StatCrunch. So those are the options that we have that we could use. I'm going to use the inverse norm command from my calculator. I'm not going to demonstrate all of the methods, but you could use any of those methods that we've learned. So if I go to inverse norm, that is second and distribution. So number 3 there, inverse norm. The area in the left tail, I want to be 0.1. My mean is 0, my standard deviation is 1 because I'm dealing with the standard normal distribution here. And that 0.1 is the area in the left tail. And so I get negative 1.28. So this critical value right here is negative 1.28. Zero's here in the middle, and this is the standard normal distribution. Now for the classical approach, what I'm going to do is I'm going to convert the results from our sample into a z-score. And if the results from our sample fall over here in this 0.1 area region, then that is unusual. That would be unusual if the null hypothesis is true. So if we end up with an unusual result, we will reject the null hypothesis and conclude that the alternative is true. So my p hat in this problem is 403 out of 1,122. So 403 divided by 1,122, that is about almost 36%. I'm going to carry that out to 4 places, so that would be 0.3592. So this is approximately 0.3592. So again, in 2001, it was 38% of adults with children that ate dinner together 7 nights a week. We just got a sample where it was about 36%. So the question is this statistically significant? Is this different enough from 38% to conclude that it's no longer 38% of families that eat together 7 nights a week? It's now less than that. That's really the idea here. Are the results that we just obtained from our sample, are those occurring because this is no longer true, or did this result just occur because I happened to get a sample that varied? Again, the way I will tell is if this result is an unusual result, which would lie in this area over here to the left, then that would be evidence to reject the null hypothesis. If not, then I would not reject the null hypothesis. So I'm going to convert this to a z-score. Now remember, to calculate a z-score, we're going to take our p hat and we're going to subtract the real p, which we're going to assume to be the p from the null hypothesis. So we're going to call that p naught. And we're going to divide that by the standard deviation of the p hat distribution, which will be the p from the null hypothesis times 1 minus the p from the null hypothesis divided by n, all square rooted. So I'm going to calculate this, and this is called the test statistic. And in fact, typically we will denote that by z with a subscripted 0. So we'll call that z naught. So this is our z-score. So in this case, that's going to be 0.3592 minus the 0.38 from the null hypothesis divided by the square root of 0.38 times 1 minus 0.38, again using the p naught from the null hypothesis, divided by our sample size, which is 1,122. So if I bring back in my calculator and type that in, so I'm going to do parenthesis on the top, 0.3592 minus 0.38, close the parenthesis, divided by the square root of 0.38 times 1 minus 0.38, close the parenthesis, divided by 1,122. And so that gives me negative 1.435. So my test statistic is negative 1.435. Now, under the classical approach, I'm going to compare that. I'm going to compare that value to my negative 1.28 that was separating the level of significance in the left tail from in the right of that. So negative 1.435 would fall to the left of the negative 1.28. So in other words, that is falling over here into the unusual results area. So if that happens, then that is evidence to reject the null hypothesis. So because, in this case, negative 1.435 is less than negative 1.28, in other words, my test statistic, Z0, is less than my critical value, Z sub alpha. Because that's true, we're going to reject the null hypothesis. So we're going to reject that the null hypothesis is true, which means we're going to conclude that the alternative is true. So our conclusion then is, so it appears that the proportion of families that eat dinner together 7 nights per week has decreased below 38%. So it was 38% back in 2001. Based on our sample evidence that we just obtained, it now appears that the percent is less than 38%. So our results were not just because samples vary. Our results was because it appears that the proportion has actually decreased. Our results were statistically significant. So now we have discussed this. This is the classical approach, and we'll make this a little more formal later on. But I want to contrast this with another approach called the p-value approach. And so we'll pick up from here in the next video.